So at the top of your notes page, there's a table that provides an overview of Chapter 8. So in 8.1 and 8.2, both of those involve building a confidence interval for mu, the population mean, and 8.3 involves a confidence interval for the population proportion. Which is P. And we'll deal with that later, but population proportion would be some kind of a statement like 90% of voters support blah 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 law, or 75% of Americans support the legalization of something or other. So when you're making a statement about a percentage of the population, that is a population proportion. If we are talking about, if there's no mention of a percentage of the population, then we must be talking about rabbit weight, and that would be the population mean rabbit weight, or the population mean age of a student, or something like that. So these would be both population mean situations. Now, in all of these cases, we are building a confidence interval that we hope will capture mu or p. And so this becomes the confidence interval that captures mu. We're saying that mu is going to be between this number and this number, and x bar is the sample mean, and then the EBM is the margin of error, or the error bound. And this is the formula for the error bound. Z times sigma divided by the square root of n, and I'll explain that more detail soon. And then there's also a calculator method that we'll use to check our results. So this will give you this this confidence interval. And if you go to stat tests t interval, then that will give you the confidence interval in the situation where sigma is not known, and we're just working with the sample mean. Now, in 8.2, we have a slightly different formula for the EBM. Instead of z, which is the same z as z-scores, we have t. And I wouldn't worry too much about this. Z and t have similar roles. Remember that a z-score of 3 means you are 3 standard deviations above the mean, and a z-score of -2 means that you are 2 standard deviations below the mean. I meant z equals -2. Then you'd be 2 standard deviations below the mean. T is really similar, and I don't really break my brain over the difference between the two, but T is what you use when you do not have sigma. When we get into the T distribution, we need to know that the degrees of freedom is n-1, and the TI-84 can also give you the T-score that you need. So I'll walk you through that process. This table is just summarizing all of the information. When we get to the population proportion, then we'll go through this process again. It's kind of similar and kind of different. There, instead of an EBM, we'll have an EBP, and this is the formula for that margin of error. And so we'll deal with that later. First, let's just look at the rest of this page. So how do we find the confidence interval when sigma is known? Now, I will be honest with you, I find this a little weird. We are saying that we don't know mu, right? We're trying to build a confidence interval. We're trying to say, oh, mu is probably between these two numbers. So that means we don't know where mu is, where the population mean is, but we do know the population standard deviation, which is a little weird to me. Why would you not know mu if you do know sigma? Oh well. We'll just go with it. There's just a little part of me that wonders about that. I do understand, however, that you might know sigma from a different and similar population and simply not know what mu is in a new population. So maybe that's what we're up against here. Now there is a requirement before we move on that we have to have either x approximately normally distributed or n equals 30 or higher, greater than or equal to 30. And the reason that this requirement is given is because in Chapter 7, we dealt with the distribution of the sample means. So we knew that x bar had a certain normal distribution, again, if the requirements were met. Let me just back this up a bit. X bar is normally distributed with a mean of mu and a standard deviation of sigma over root n. And the connection between Chapter 7 and Chapter 8 is that once we know how the sample mean behaves and how much variability it has, then that enables us to predict how wide of a margin of error we need. So the little story I made up for us here is that you're trying to estimate the population mean rabbit weight, mu. So you sample and weigh 50 rabbits. You get a average weight of 680 grams. The population standard deviation, sigma, is 75 grams. Find a 90% confidence interval for the population mean rabbit weight. Now I've organized the given information. All of the given information in the problem I've organized here in the need column. We need to know the sample mean. X bar was 680 grams. The sample size n was 50 rabbits. The confidence level is 90%, so we write 0.90. And finally, sigma is given to us. It's 75 grams. So we needed all four of those pieces of information. And now we're going to go through these 4 steps in order to get the confidence interval for the population mean. So you'll see here that I've written that z is equal to 1.645, and that is based on the confidence level. If we are looking at a confidence level of 90%, then the z-score will be 1.645. And the z-score gets bigger if we raise our confidence level to 99%. And I recommend that you copy this table onto your notes sheet. I will explain to you in the slides coming up how I got those values. It's kind of convoluted. It is understandable, but it's like a 3-step process to figure out to go from the confidence level to the z-score. So in the interest of time, you might want to just reference this and copy it down. So the z-score is based on the confidence level, and I will refer to that z-score as z alpha over 2 sometimes. And again, that will make sense after we look at those slides. The next thing is, what is the EBM? Well, the formula I gave you above said that EBM is equal to z times sigma over root n. So there's your z, 1.645, times sigma, 75, divided by root 50. So that's what we're working out. And when I punch that into my calculator, I get 17.448 is my EBM. Cool. So now I can do x bar plus or minus 17.448. The confidence interval is x bar minus the EBM, comma, x bar plus the EBM. And that's what I've done here. We estimate, here's my interpretation, we estimate with 90% confidence that mu, the rabbit population mean, is between 662.6 grams and 697.4 grams. I got rid of a little bit of accuracy, that was too cluttery. So I'm 99% confident that the population mean is between these two values. That's a fairly large margin of error, but it's reasonably good, basically between 660 and 700. So fairly decent precision, but again, I could repeat the process with 95 or 98% confidence just to increase my confidence level. If I did that, unfortunately, my interval is going to get wider. The only way to be more confident is to have a wider interval. Now, again, I'll show you a slide about this, but if we repeated the sampling process 100 times, which we probably don't have time to do, but this means going out and weighing a bunch of rabbits and getting a sample mean. Going out, weigh a bunch of rabbits, get a sample mean. If you repeat that process 100 times, 90% of those times we would capture the population mean in the interval. So there would be 10 times where our interval doesn't contain the true rabbit population mean, but 90% of the time we will. So that's what the 90% confidence level means. And then finally, I will show you in the next video how to use the calculator to check your answer for number 1. And I'm thinking that this isn't available on the TI-83. It's only on the TI-84, which is a little bit of a bummer. But anyway, oh no, this one's going to be available on both because it's the Z interval. It's the T interval that may not be available on the TI-83. All right, so I'll do this process in the next video.